Hi everyone, I welcome you all to this lecture of fluid mechanics. So yesterday studied, we have started the viscous stresses and the drag, Stokes drag. And in the concept of viscosity, I want to add few things here in this lecture. So when I am discussing about this, so just want to put the SI unit of viscosity is Newton second per meter square, and the CGS unit is Dine second per centimeter square, which is also equal to poise. Okay. And there were few questions that were asked on the dimension of viscosity in general. So you can calculate the dimension of viscosity from here. The dimension of viscosity is nothing but dimension of shear stress. So dimension of shear stress is force per unit area. So dimension of force is MLT minus 2 divided by L square. That is dimension of shear stress or the dimension of pressure. And the dimension of this is LT minus 1 divided by L. The dimension comes out to be it's MLT minus 2. So M L minus 1 T minus 1. So that's the dimension of viscosity. Another thing that I want to point out is, so here I am denoting the viscosity to be mu. You can also denote it with theta. Okay. And that's all. So before going to the Stokes drag, let's discuss one question that is based on NCERT related to the concept of viscosity. So the question is like this. So here we have a block that is, and there is a tension in the string. There is a pulley. So that diagram is given in the question. Okay. And there is a fluid. There is a fluid layer inside this. So in between this solid block and this surface, there is a fluid layer inside this. So the question is, and this the area in contact with liquid is 0.1 meter square. The weight of this block is 0.01 kg. So the question is, a metal block of area 0.1 meter square is connected to a mass of 0.01 kg via a string that is passes over an ideal pulley. A liquid with a film thickness. So the film thickness is 0.1 mm is placed between the block and the table. When released, the block moves to the right. So as it goes down, it moves to the right with a constant speed of 0.06 meter per second. Find the viscosity of the fluid. We need to find out the viscosity of the fluid. Just for a hint, So I told you that shear stress is eta dV by dz. So this dV by dz can be calculated as like this also. And this shear stress is force per unit area of the contact area. Okay. So you can try this then I will solve it in one go. Okay. So let's discuss the solution. So as I told you many times, that's for any question in physics. If you know how to make a free body diagram, then you can solve any question. So for that, you can make a free body diagram of this block. So this force is like mg. Here in this direction, this is tension over here. So from here, what we get is T is equals to mg, that is 0.01 into 10, that is 0.1. That is tension. Now this tension is pulling this. So this is the force that is acting on the block. Or if you can zoom out, that it's look like a fluid is in between between the two plates. So if you zoom it out, if you zoom this out, then it's look like this plate is moving with velocity. The force is applied, and the velocity of this top plate is 0.06 meter per second. The table is still, so the table is not moving, such that so the table is not moving. So you need to we know F. So here is a fluid. So now this force, and at this point, because it is still, so velocity of fluid here is 0. So delta V you can calculate, that is 0.06 meter per second, and delta Z is, so if you consider this direction to be Z, then delta Z is given, that is the film thickness, that is 0.1 mm, 0.1 into 10 to the power minus 3 meter. So we have this. Now apply this formula. That is force per unit area is nothing but eta into del V by del Z. So force is this tension, that is 0.1 Newton. Area of contact is also 0.1. Eta we need to find out. Delta V is 0.06. Delta Z is 0.1 into 10 to the power minus 3. From here we can get eta. Eta comes out to be 0.1 divided by 0.06 into 10 to the power minus 3. So 10, 100, that comes out to be 1.7, around 7 into 10 to the power minus 3. And the unit is in Newton second per meter square. Or the unit can be Pascal second. Okay, so that's the answer. That's about the law of viscosity. Now let's come back again. So I will remind you the Stokes drag. So Stokes drag tells us about the friction that a body feels when it is moving in any fluid. Either it's due to any forces, whether it's gravity, whether it's electric field, whatever it is, but it feels a drag, and that drag opposes the motion of this body. And I told you that Stokes has come up with this with this derivation of viscous drag, and found out that FD is equals to 6 pi mu RB, or you can write it as just now I told you, because in NCRT its mu is eta, so it's eta RB. And so with the help of dimensional analysis, we can see that how this formula came. The derivation of Stokes drag via dimensional analysis. Okay. So we know that the drag force is directly proportional to, or according to Stokes law, I can write viscous drag directly proportional to shape and size of object, directly proportional to speed of object, and directly proportional to the viscosity, eta. So consider a spherical object freely falling in a viscous fluid. Find out the drag acting on it. Okay. So as I told you, viscous drag. So for a spherical, it will be directly proportional to the radius of the object, because shape for different object it is different. So if there is a cube, if there is a cylinder, so the characteristic length, and we generally call this length to be a characteristic length that defines the shape and size of the object in the fluid. Velocity of the object and viscosity of the object. So by dimensional analysis, we know that Fd is R V eta. Let's put the dimensions. The dimension of this is ml p minus 2, directly proportional to L lt minus 1. Eta is Pascal second, that is mlt minus 2. So eta is m L minus 1 t minus 1. We have just calculated that. So that we don't know what is the proportion alpha beta gamma. Let's put it alpha beta gamma. We need to calculate alpha beta gamma. So mlt minus 2 to L alpha plus beta plus gamma. P is minus beta minus gamma. L, T and M is gamma. From here, gamma comes out to be 1. Alpha plus beta plus gamma comes out to be 1. And minus beta minus gamma is minus 2. So gamma you can put it here. So minus beta minus 1 is equals to minus 2. So beta is 1. Gamma is 1. Alpha is, that is alpha plus beta, sorry, it's minus gamma. Alpha plus beta minus gamma. Yeah, it's minus gamma. Minus gamma. So alpha plus 1 minus 1 is equals to 1. So alpha comes out to be 1. Okay. So Fd is directly proportional to Rv eta. So Fd is Arv eta. But from the dimensional analysis, we don't know what is the exact proportionality constant. But according to Stokes law, it is 6 pi eta Rg. The proportionality constant is 6 pi. This is the simple way to check with the dimensional analysis. Not always the correct way. It will give you a rough estimation of different dependence on different variables. Okay. Now moving ahead, so there is a concept of terminal velocity. Terminal velocity is, so it is, first I will be writing a definition. So it is defined as the highest velocity attained by a body freely falling in a viscous viscous fluid when the sum of drag force and upthrust is equal to the downward gravity acting on the object. Okay, so let's consider a pool of liquid, of viscous liquid. So considering a pool of viscous liquid in which a spherical body is dropped. It's a viscous liquid, and a spherical body is dropped inside this, such that the density of, so we, for now we are considering the density of this body is rho s, the density of fluid is rho f, and rho s is greater than rho f. And after some time, what will happen? So this mg, and there is a upthrust, it will reach equilibrium. I'm just adding this in the definition also, acting on a budget, and it reaches the equilibrium. Okay, so upthrust is acting in this direction, and the drag, viscous drag is also there now. So according to this concept of terminal velocity, upthrust plus viscous drag should be equals to mg. So from here we can get the velocity. So upthrust is density of fluid into volume of a sphere into g plus drag forces 6 pi eta rv. So velocity, this velocity is the velocity of the object, is equals to mass, that is rho solid, into v into g. Okay, we need to find out v. So that is terminal velocity. So that comes out to v g by 6 pi eta r rho s minus rho s. Okay, so volume of a sphere is 4 by 3 pi r cube, substitute there. So v is 2 by 9 r square by eta rho f, rho s minus rho f. So now the question is there a possibility that the terminal velocity can be negative? Yes, it is possible. Terminal velocity may be 0, may be greater than 0, and may be less than 0. So look at any question with the open mind, because it is directly proportional to the rho s minus rho f. So if the density of solid or that object that is moving inside the fluid is greater than, it may not be always the solid, it is the some object, some bubble also. So if it is greater than rho f, then terminal velocity is positive. If rho s is equals to rho f, then it's 0. It will float. If rho s is less than rho f, then terminal velocity is negative. And that is for the example, if you have a bubble a bubble of water. So the density of bubble is basically the air. So when it's a bubble, so the density of a bubble is around 1.2. So that is less than the density of water. So we have seen that bubble rises in a fluid. Now let's look at one question related to the terminal velocity. So that is JE question, JE advanced. So we have two pool of liquid. Let's call it as A. Another pool of liquid, that is B. So we have two pool of liquid. So rho F A is given to be 0.8. Rho F B is 1.6. Both the solid object are same. That is rho solid. Both the rho solid are same. That is of density 8 gram per centimeter cube. These are also gram per centimeter cube. Gram per centimeter cube. Viscosity of this fluid is eta here is 3, eta here is 2, 3 points and 2 points. That is very highly viscous fluids. Diameter of this sphere here, diameter of the object here is 1 centimeter. Here is 0.5 centimeter. So we need to calculate the question is calculate the VA by VB. Options are 1, 3, 2, 4. So take 1 minute and then we solve this question. Okay. So we need to find out the ratio of the velocity, terminal velocity in fluid A and in fluid B. Okay. So what we can do is we know the formula of terminal velocity in A, that is 2 by 9 R square rho solid minus rho fluid by eta. So rho solid is same for both. So that is rho FA and eta A and RA. Similarly, VB is 2 by 9 RB square rho solid minus rho FB by eta B. So VA by VB is RA square by RB square rho S minus rho FA divided by rho S minus rho FB eta A eta B. So let's put the value. So RA by RB is nothing but by RB is dA by dB, that is 1 by 0.5, that is 2, that is 4. Rho solid is same for both, so that is 8 minus fluid 1 is 0.8 divided by 8 minus 1.6 into eta B by eta E. Eta B is 2 divided by 3. That is 8 by 3 into 7.2 divided by 6.4. So that is, it comes out to be correct option is this. Okay. Let's take one more simple question. So the terminal velocity of a copper ball of radius 2 mm falling to a tank of oil. Tank of oil at 20 degrees centigrade is 6.5 centimeter per second. Compute the viscosity of the oil at 20 degrees centigrade. Density of oil is 1.5 into 10 to the power 3 kg per meter cube. Density of copper is 8.9 into 10 to the power 3 kg per meter cube. Okay. So we need to find out the viscosity. Options are 9.9 into 10 to the minus 1 kg per meter second. 9, 8. Try this question. Okay, now solve this question. So we have given a terminal velocity that is 6.5 centimeter per second. Diameter of the radius of the copper ball is 2 mm is equals to 2 into 10 to the minus 3 meter. That is 6.5 into 10 to the minus 2 meter per second. To convert everything into SI unit, that is the best way because the final answer is also in the SI unit. Okay, so that is this. Then G is 9.8 meter per second square. In all the lectures, it is there. Hello, is it there in all the lectures? Okay, so we have a terminal velocity given. So we have converted it into the SI units. Then radius is there. Then G is there. And surface tension. And we need to find out the viscosity. The density of oil is 1.5 into 10 to the power 3 kg per meter cube. And density of copper is. So we need to find out the terminal velocity. So terminal velocity, the formula is, I have already derived the velocity, terminal velocity formula, that is 2r square by 9 eta into rho solid minus rho fluid, and terminal velocity is given, that is 6.5 into 10 to the minus 2 meter per second. 2 into 2 into 10 to the minus 3 square into rho s minus rho f, that is the rho s minus rho f is 8.9 minus 1.5 into 10 to the power 3 divided by eta. So from eta here, you can solve it. You can do the calculation. I'm just writing the answer. So that comes out to be 9.9 into 10 to the power minus 1 kg meter inverse second. So the correct option is this. Okay. So that is all about the concepts of drag and terminal velocity. Now let's move ahead. Okay. So we have done with the concept of terminal velocity is considered right. Now let's move on to the last concept of this, that is surface tension. Okay. So I am giving you some example before discussing the concept of surface tension or the interfacial tension that you can see around yourself. So you may see that you may notice that oil and water do not mix. I am just giving some example to get a feel of surface tension. Water wets us, but not the ice. Mercury does not wet glass, but water sticks to it. Oil rises in a cotton pick. You can see that there is a if we just put this thin wick of cotton in a oil, so it gets rises. I told you that's why we have used mercury in the measuring instruments. Soap and if you see that a brush, paint brush, so initially it's like this. There are hairs of brush. When you dipped it into the some liquid, it gets wet, and after dipping, what you get is the surface tension reduces. So the surface tension, due to the surface tension, the area of this becomes like this. So these thread like take a conical shape with a fine tip that are also thread. That is the effect of surface tension. So basically any free surface acquired by any free surface has having a surface tension. Okay. So before going to next part, I am giving you one question and try to solve it. So we have a sphere and of radius r and a cube. We have a sphere and a cube of length a. Both have same volumes. Both have same volume. Calculate the both have same volumes. Calculate the surface area. Surface area in terms of volume and suggest which of these are having a minimum surface area. Okay. Okay. So I am giving you this question. You give your arguments. So options are sphere has higher surface area. Cube has cube has having higher surface area. Surface area of both the sphere and the cube is same and D none of the above. Okay. We will discuss in the start of next class.